Imagine sending a request to a website and having it secretly hijack someone else's session, trigger an admin action, or even worse, bypass authentication, all without them clicking on a single thing. That is HTTP request smuggling, a vulnerability that doesn't live in the front end or the back end, but it lives in the gap between them. And when that gap gets exploited, you're looking at full cache poisoning, credential theft, and even sometimes full domain takeovers, all from a single weird looking HTTP request. And to even dig deeper, I invited James Kettle, who has done more to push this bug forward than anyone else that I know, to join me and help me break this down. So I did an interview with him. We're going to first talk to him about how he approaches this research, what are the things that he looks for, and then we're going to do some hands-on demo of all of this in action. So how do you choose which technologies or RFCs to focus your research on?
So, in terms of the tech or the topic, uh, if you've been researching for a long time, you just kind of instinctively know because you've seen things, you've seen all these clues over the last 5, 10 years. Um, but if you're coming into it with less of a background in research, I think basically any topic that you're scared of, anything that makes you nervous, anything you're not comfortable with, uh, that is a strong indication that that topic it has research potential and is worth exploring.
With HTTP being so old, what do you look for in these RFCs that signals this could be vulnerable? I want to rip this thing apart.
So there's so much in RFCs. That's why I love them so much. The first thing I would say is I like to look at the oldest RFCs. Like people will tell me off because I cite RFC 2616 because it's deprecated. But the thing is, the servers were implemented on that RFC, and then a new RFC came out and said you need to do it differently. But RFCs never break backwards compatibility, right? So those servers kept working, and no developer ever looked at the new RFC that has like more safeguards and so on, and did that. So look at the oldest available RFC, and then inside them, one good thing to look for is forgotten functionality. Like, for example, take the connection header. Everyone sees connection keep alive on their requests, right? But then you read the RFC and it says HTTP proxies must remove any headers named by the connection header. And it's like no one browsers never do that. Clients never do that, right? So no one realizes that HTTP even has that capability. And then as soon as you see it, you're like, oh yeah, that would be really useful for request smuggling.
So, are these forgotten features what actually kickstarts your research? Like, tell me a little bit more.
I think like they provide it's a good way to start like it's a lead into the research. It kind of raises questions like you see that you might see a sentence like, yeah, you can use the connection header to remove other headers. And then you have follow-up questions instantly like, does servers actually support this? And then what happens if I remove the content length header? What happens if I use the header to remove itself? What if I remove a header that doesn't exist? What if I remove a trailing header? Like it instantly, every every little thing you read sparks another five ideas, and then it's a matter of kind of trying to guess which ones are actually worth investigating. Uh, yeah, so forgotten functionality is super useful, and the other main source of useful stuff is forbidden actions. Anytime the RFC says like, uh, for example, the HB2 RFC says any message containing connection specific header fields must be treated as malformed, and they don't say why. But you know, if they said this must be treated as malformed, there's probably a good reason. And if you can reverse, but basically you're reverse engineering the brain of the RFC author, and you're going, why did they say that? And in that particular case, that was in the HB2 RFC, and Amazon's application load balancer didn't obey that, which meant that they didn't remove the transfer encoding header when you sent it over H2, which gave me request smuggling on basically everything behind Amazon, uh, which was nice. So you can see if you can infer why they said don't do this, often it's because things are going to get hacked.
What should someone focus on if they want to really understand and get good at request smuggling? Like, where do I start? What do I do?
I think the main thing that people don't understand very well is HTTP keep alive and HTTP pipelining. Uh, and it's like it's only when you properly understand that the request smuggling really makes sense. People think because all the tools represent HTTP requests as these kind of standalone isolated things, but in fact, HTTP requests go on a stream, right? It's just like they just go over TCP or TLS, and it's just a stream. They're all just stuffed there back to back, and tools never show you that view. But that view is like the fact that actually there is no boundary between one request and the next request, at least with HTTP one. That is what makes the whole attack possible.
Okay, can you tease a little bit about your upcoming research for Black Hat and DEF CON?
Yeah, sure. So when I write the abstract for a talk like that, I put all the best teasers I can think of in there. But actually, we made quite a lot of progress with this research after the abstract was written. And now the total number of websites that we were able to compromise is in the vicinity of about 30 million.
30 million. How would you categorize it? What kind of technology are we talking here?
Basically, originally the answer is multiple CDNs.
Now that we have heard how James approaches RFCs and his process for research, let's break down what actually is going on when we talk about HTTP request smuggling. Before we jump in, do me a favor. If you're into this kind of content and you want a full breakdown in a course format, just drop a comment that says course. If enough of you ask, I'll put together a free step-by-step walkthrough to take you even deeper. All right, let's jump into it. But to understand it, we've got to take a step back and look at what happens under the hood when we actually visit a website. When your browser sends a request to a website, it uses HTTP protocol, which runs on top of TCP. And that is very, very important. Think of TCP as a tunnel. HTTP requests are packed into this tunnel, sent to the server, and then the server sends responses back through that same tunnel. In the older versions of HTTP, like 1.0, that tunnel closed after each request and response, a one and done deal. And that is really, really slow. So along came 1.1, which is still widely used today. In HTTP 1.1, TCP connections are reused. You might send 5 requests to the same site. They all go through the same TCP connection. That's efficient, but it opens up the door for a lot of weirdness. Now, when you visit a website, your request might pass through a front-end server, like a CDN, a load balancer, or even a reverse proxy before reaching the back-end server. Both ends, front and back, are sharing that same TCP tunnel. But here is what happens, and here's the twist. Your request to the front end is isolated. It's just you, but when the front end talks to the back end, it might be using a tunnel that's shared by multiple users. So what happens if the front end and the back end don't agree on where one HTTP request ends and the next one begins? That is where request smuggling comes in. So let's quickly talk about what is exactly request smuggling. Request smuggling is when you send a specifically crafted HTTP request that's interpreted differently by the front end and the back end servers. One server thinks the request ends here, while the other one thinks it continues. Boom, that is our desync. In that gap, an attacker can smuggle in extra data, maybe even a second request. And I know what you're asking, why does this happen exactly? Well, this usually happens because of how HTTP defines the body of a request. There are typically 2 main headers that control this. The content length, which says this request body is exactly 100 bytes. And the next one is transfer encoding, which says I'll send you the body in chunks. Keep reading until I send a chunk of 0 bytes. Both are valid, but you're not supposed to use them together. And if you do use them together, the servers might disagree on which ones to trust. On one end, the proxy may say, okay, I did 100 bytes, we're done. While the backend says, wait, I'm using chunked encoding, I'm still reading. And that right there is your smuggling opportunity. And honestly, this isn't just some low impact vulnerability. It could be devastating. A successful request smuggling attack can do a lot of damage, like bypass authentication, trigger internal admin functionality, hijack another user's session, poison web caches, deliver reflected payloads that normally wouldn't be exploitable, escalate boring bugs into high impact vulnerabilities. And in some extreme cases, you can perform arbitrary response generations, meaning you can make the backend respond however you want it to. That one is a bit more advanced. We'll come back to that one in a future video. And for those of you that are bug bounty hunters, this is where the money comes in. Bug bounty programs love request smuggling, mostly because they hate when they miss it. It is super subtle, it's quiet, and it doesn't show up in the logs. But if you can show you've bypassed authentication, hijacked a session, or abused a vulnerable internal API, those are all critical vulnerabilities. And that also means serious bug bounty payouts. Now, real quick, content length and transfer encoding are just the tip of the iceberg. They are the ones that everyone learns first, but there are a dozen, maybe hundreds of edge cases that can trigger a desync depending on how servers parse the HTTP requests. This is the kind of thing that James is digging into in his latest research, and hopefully we'll cover all of that in a follow-up video. Now, let me show you a cool example that shows how even a simple GET request can cause problems. Some backend servers assume GET requests never have a body and just ignore it, but a proxy might honor the content length and forward that body anyways. So it looks something like this. To the proxy, that is a single big request, but the backend sees the second part as a brand new smuggled request. This kind of technique can turn a non-exploitable reflected XSS into a fully weaponized exploit with zero user interaction. All right, if you've made it this far into the video, congrats. You're probably ahead of most people that still don't understand HTTP request smuggling. With that said though, I want to make sure we go to one of these labs that covers everything that I've talked about throughout this video, and that is the CLTE lab on Portswigger's Academy. We're going to launch it. I'm going to show you everything that I've talked about so far in action. But before we jump into the lab really quickly, this is a great resource for everything request smuggling that you want to learn. If you look right here, they also link you to all of their previous research that they've done at DEF CON and Black Hat. Honestly, if you want to learn more, this is the place to go. But for this lab example, we're going to do the exploiting request smuggling to deliver reflected XSS. And if you remember, earlier in the video, I talked about how you can abuse this to take a self XSS and deliver it to another victim or a user on the website. And this is a prime example of that in a lab format. So we're going to launch this really quickly. And what I'm going to do here is I'm going to turn on intercept, send a request here, send it to my repeater, turn it off, and just send the request so we can see the response. And if we look at it here, we can see that our user agent should be reflected somewhere here. Maybe it's not on this page. Obviously, I've done this lab before, but I want to show you how it looks so you can understand where the vulnerability is. You can see right here, there is a value that is being set to Mozilla 5, which is our user agent. So if I go to this page right here, we can see that there is a reflected XSS. But the trick here is that this XSS is unfortunately only exploitable to ourselves. So if I put test123 here and I look for it, it is going to show up here, and we can obviously exploit this by closing the tag. And now we have injected something in there. We can inject more in there, but unfortunately this is going to only be exploitable with a man in the middle if we can inject some text into the user agent. So we want to take this attack and try and see if we can do some request smuggling in order to do this to our victim. And let me show you how it's done. So to identify request smuggling, one of the most important things is to understand how the proxy behaves. We need to figure out which header the front end trusts first. Is it the content length or is it the transfer encoding? There are a few ways we can do this to detect it, but the basic idea here is to send different requests with different bodies, different content length, and also using the transfer encoding header, and observe how both the front end and back end respond. All right, let's take a look at this example really quickly. What we're going to do here is we're going to get rid of all the different headers here that are extra that we don't need, just to clean up our request. And we're going to change a couple of things here. One is we want to make sure that we are doing HTTP 1, because that's what a vulnerability is. And we want to make sure that this request works. If I send the GET request, perfect, it works. The second thing is we want to flip this to a post request, but also make sure that works as well. Perfect, this works. We have everything we need. Now we need to take a look at those behaviors and see if we can figure out which one of those headers is being used first. And the way to test this out is we want to make sure we have both of these headers present, and we ended with a 0 and a new line. I'm just going to actually make this be visible like this. So we have our characters, but what we're doing here is we're sending a post request with the body or the content length set to 0. So what happens is when the front end receives this request, it looks at content length and says, hey, I'm expecting 0 bytes here. So whatever you put into here, it's going to get ignored. But when it gets to the back end looks at the transfer encoding and it's looking for this 0 that was not sent from the front end to terminate this request. And because the way to terminate this chunk request is to have this ending 0 that tells, hey, this is terminated, it's over. So if we're setting this to 0, it is not going to send this and receive it, and it's going to cause an error right here. And you can see right now, Looks like there is an issue here is because we updated the content length. So we got to make sure we disable it and set this to 0. And now if we send this, we can see that this is not being passed to the backend, and it is expecting for this 0 to be there, and at some point it is going to cause an error for us. So that's one way to verify that the content length is being used first versus the transfer encoding being used in the backend later on. But now let's flip that. What if the front end is using transfer encoding and the backend is using content length? Well, the way to do that is simple. We can just add an extra character here, and now the content length is 6. This is 1, 2, 3, 4, 5, and 6. So we can put that into 6. This won't work with this lab because it's not actually, the transfer encoding isn't being used first, but I'm going to show you how it works if that was the case. What happens here is when the front end receives this, it says, okay, I'm going to use transfer encoding first, and you're indicating that this request ends right here with this 0. And you're sending 6 characters, which is these 6 right here. I'm going to just end this request and send all of this to the backend and ignore this. I'm going to store this somewhere else. We don't care what happens to it, but we're going to send this request to the backend. But what the backend receives here is a post request, but with only 5 characters or 5 bytes, even though it's expecting 6. So this reason, it's going to send us an error. So this is how you can tell where the front end is using the content length versus the transfer encoding. This is really, really important for us to know. We need to determine which one is being used first to make sure our exploit works properly. So now that we understand everything, we're going to send the proper request with the right content length, which is 5, because we're sending this ending 0 for the transfer encoding, and then followed by these 4 other bytes. So it's 5 bytes. And if we send this, we should not be getting an error because the front end is saying, hey, you're going to send 5 bytes. And these are the 5 bytes that we're sending. And then when it gets to the back end, which is expecting the transfer encoding, it receives this ending 0 that says, okay, the request ends right here. And everything is going as we expect it to. But now what we want to do is we want to try and smuggle a request into the next person that visits this website. So if I put something like this here and we actually successfully smuggle this request, they're going to get a 404 because this page hopefully doesn't exist. So when they go to the web root, instead of going to their expected page, they're going to see the results of this request instead. And if we send that right now, it's going to do its thing. It actually is not going to do its thing because we need to make sure we update the content length. So it updates with whatever we put here. So we're going to send that one more time. It looks like the request was sent. So now if I do this one more time and we just do a get request as our victim, we're going to get an error. Let's make sure we remove all these. We don't need it. Let's send that one more time. We can see that it says invalid request. And the reason why it's getting a 400 bad request with an invalid request is because even though we've smuggled something here, it isn't properly being done. And let me show you why. Let me show you what happens when this request is being smuggled for our victim. So this is the request that our victim is sending to it, but somehow they're getting an invalid request. What happens is when we smuggle our request and we put ours before theirs, the backend is going to receive this. So that means there's 2 get requests. One is being sent to not found 404 and the other one is being sent to the web root. So there's 2 here, and the backend is going to get very confused and say, hey, which one do you want me to use? And to get around this issue, all we have to do is end our request with a unfinished header. This could be anything like X ignore me. So everything gets appended here. In reality, what happens is that when we send this request and our victim's request, this header is going to get added and their original request is going to be just in this ignore me header, and the server is not going to just do anything with it because this doesn't mean anything to them and it's going to skip it. So if I do this right now, we actually make sure we have the right request for our victim. This is our victim. This one is our attacker. So if I send this right now, no error, and we go into here and we send the same request, and now we can see that we're getting a not found. So now we have been able to successfully hijack their request, send them to what we want, and is whatever they were sending originally is getting ignored based on our smuggled request. But now it's not over. We need to exploit this XSS, and that's when all of this gets really interesting. So if we remember correctly, the vulnerability existed in this post ID equals 8. And if we look for our user agent, and make sure I'm not intercepting, there we go. It's going to take a minute. If we look for our user agent, we can see that it's being shown here, but it only works on post ID 8. So what we want to do here is we want to make sure that we are grabbing this post request or that post endpoint, and we're adding it to here. And instead of sending our user agent that says test and closes out the current one, and then we add a script alert 1 with a closing script. And if we did everything right, it's going to smuggle whatever request they send. It's going to send it to this one instead, replace the user agent, exploit the XSS, and it is going to give us an alert 1. So we send this request, we smuggled it, so we go back into it, and if everything worked, the next person that visits this page is going to get an alert 1. So we refresh, and we can see that we got an alert 1, which helps us solve this lab, and now we have been able to successfully exploit an XSS that was not exploitable without this vulnerability. The thing that you have to keep in mind is when you smuggle a request, it is going to get smuggled for whoever sees that page next. And if it's not you and somebody else visits that web page before you do, and you check your POC, they're going to get the alert 1. So the way to exploit this in masses, you just want to run a script, you use intruder or run something with Python that has this request being sent continuously. So every time anyone visits this, including you, is going to get that alert 1. So keep that in mind. It just comes with a first come, first serves, unless you keep smuggling more and more requests. All right, that's it. That was request smuggling, a complex vulnerability that doesn't rely on flashy payloads or browser-based exploits. It lives at the protocol level, buried in how different systems interpret the same request. Once you understand how those tiny parsing mismatches create desyncs, you start to realize just how powerful and subtle this bug really is. And with new techniques emerging all the time, it's one of those vulnerabilities that's only getting more interesting. And if you're watching this during DEF CON, stay tuned. James is just getting started. All right, that's it. I'll see you all in next week's video. Peace.